So what happened in the last demo? You assumed that the initial condition was along the eigenvector, and then you played with the eigenvalue. And you saw if the eigenvalue was above 1, the activities of both neurons went to infinity. If it was between 0 and 1, the activities decayed to 0, to the origin. If the eigenvalue was between -1 and 0, the activities jumped across the origin but eventually decayed to 0, so they kind of jumped like this. And if the eigenvalue was below -1, again, there was jumping across the origin, but the activities got bigger and bigger in terms of being closer to negative infinity or positive infinity and eventually explode. And all of that, you could have actually guessed just by thinking through this equation. So the activities at a time are equal to the eigenvalue raised to that time power times the eigenvector. So if you have an eigenvalue above 1, a value that's above 1 to the ith power will be huge. So that's why the activities explode, because this becomes huge. If it's between 0 and 1, like let's say it's 0.5, it becomes smaller and smaller at higher powers. So that's why it decays to 0, because this number becomes tiny. And then with negative eigenvalues, it's the similar distinction between 0 and -1 and below -1, but now it's jumping across the origin because, as a simple example, if you look at -1, -1 to odd powers is negative and even powers is positive. So it's jumping across to basically complete opposite directions of the vector based on that. So we just looked at a very specific initial condition, which was along the eigenvector. What happens if there are other initial conditions that you start with, so anywhere else in space? And it turns out that we can actually write the activity as a basis, or using a basis that is the eigenvectors. And this is true for this matrix because, as you can see, these eigenvectors are two linearly independent vectors in 2D space. So they span 2D space and are a basis for it. So this is way back from tutorial 1. Hopefully you still remember. So we can write the activity at time point 0 as a linear combination, again, something from tutorial 1, of the two eigenvectors. And so this is true of any initial condition we pick. Anywhere in this space, we could write it as some scalar times the first eigenvector plus some scalar times the second eigenvector. And so if we then do what we've done before and start substituting in, we get the activities at time step 1 are equal to the weights times this linear combination written out. And then we can perform basically algebra on that to rewrite it into this form. And so that's pulling the constants out front and then using the fact that they're eigenvectors to turn this into the eigenvalue times the eigenvector. So we get the activity at time point 1 is the constant times the eigenvalue times the first eigenvector plus the second constant times the second eigenvalue times the second eigenvector. And I do apologize, this is a lot of math on the slide. So in general, if we kept writing it out, we would see that, again, we can write a general equation. So we can write the activities at time bin I are equal to the constant times the eigenvalue to that ith power times the eigenvector plus the second constant times the second eigenvalue to that ith power times the second eigenvector. So what happens to the activity matrix will once again really depend on the eigenvalues and the eigenvectors, because now you can start to think about the vector addition geometry that we thought about before. If this was really huge and this was really huge, the activities will again explode to infinity because it's a huge vector times a huge vector, plus a huge vector. If this is going to 0 and this is going to 0, it would also decay to 0. And so once again, the activities really depend on the eigenvalues. There's just the added complication that now it depends a little bit on the eigenvalues and what exactly the initial condition is. And so you'll play with that in the next demo, where now it will be the similar demo as before, but now you can change both eigenvalues and the initial firing rates, and you can observe that resulting population activity over time.